So this is a simulation, and I think with equilibriums, the best thing to do to try to understand them is just to watch them in progress. I really like the simulation because it's simplified, but it doesn't follow one of the rules of chemistry in terms of the letters. So if you look on the top left, you'll see the green A. That represents all reactants. And you'll notice that if I add reactants to the system, they all fall on that left-hand side of that arrow, and they're all supposed to be like a white-greenish color. Then you'll notice at the top, you'll see a B. So that represents products. And so when I put the products in, trying to get to do it, notice that they fall over here on the right-hand side. All right. So if you look at the top, what we're saying is that A turns into B. And I know that doesn't really follow the chemistry rules you've learned so far, but just go with it and just know they're trying to keep it simplified. The stuff on the left is turning into stuff on the right. And you'll see there's a thermometer, and I can adjust the heat controls on the system like that. So I'm going to put some A in. I'm going to put 10 of them in. So if we watch this for a minute, and some of this involves being patient because it takes time to establish equilibrium. That one almost went over, but when it goes over the arrow, you'll see that it's going to turn into products. Now you'll notice that right now we don't have any reaction at all going on. So let's give it a little heat to kind of help it bump over that reaction barrier right there. So I'm going to get it up in temperature a little bit. Keep going up in temperature. And there we go, our first product. And you see what that product just did? That is equilibrium. So hang in there because it's going to take a minute for us to get our equilibrium established. So we've got one product bouncing over there on the ruler. Oh, there's our second product. Oh, we got a few products going on here. So there's our temperatures varying a lot. In a normal equilibrium reaction, we keep the temperature steady, so it's not jumping around that much. But as we watch this, there's going to be an amount of product at a specific temperature that it wants to maintain before turning over to reactants. So I'm kind of seeing right now, like, okay, there's 5 at the moment, but then it goes down to 4. And then now we're sitting at 4. Everything seems happy. It's trying to go back and forth. So the ratio might be like 6 to 4. Now we just put one over, but then it just jumped right back. Now we've got a few more going over, but let's see if fairly soon if one won't convert back. Now we're at 5. But the idea here is that this is a constant process, a constant motion. It's not like the reaction stopped at a certain ratio of reactants and products. It's a constantly moving process of products turning into reactants, turning back into products. And although this might be annoying if you've got your idea on discovering the very, very best drug in the world that will solve all of the problems, and you're trying to get a good yield, you can't get a good yield because it keeps turning into reactants. It's also really good for your body because your body needs to maintain homeostasis, and a lot of the systems in your body are actually equilibrium reactions because they have that capability of swapping back and forth as needed to maintain the body. So this right here is equilibrium. And if you add in more reactants or more products, you will still be maintaining that same ratio. Like I said, it was like around like 4 to, maybe right now it's at 5 to 5 or 4 to 6 or whatever it is. It does not have to be even. And in fact, it rarely is even. It's going to be either more reactants or more products. It's very hard to get these to turn out to be even. So let me show you how we represent this. One way we represent this is just on a line, and we pick a point of what we call equilibrium. And so right here, maybe this is where it's established. So instead of like doing like a little barrier, and I could have totally done a barrier, and that would have been probably just as clear. I can make this into a barrier if that helps. But what we're really representing is the point at which your equilibrium ratio. So this is a ratio of products to reactants. And there's more to it to this, but I'm going to leave it like this for now. So product to reactants. And so if you are like starting a reaction and you haven't had enough time to reach equilibrium, you're going to be like maybe like on the timeline of the reaction, you might be like right here. You have to get the ratio all the way to this point before you've reached equilibrium. So I'm not saying that this is only reactants. I'm just saying that the ratio isn't right here. It has to get all the way to this point to get to the right ratio of products and reactants. You also can have a reaction at equilibrium, and you can have mismeasured something, or you can get some products that you have maybe in a jar and add some extra products too. So you actually can be past the point of equilibrium if you have personally added in extra product. And so you can be like on the other side where the ratio is too big. So this would be too much product per reactant, and this is too little product per reactant. Anytime we are not at K, we are at another letter, and the other letter represents the same thing as K. It just means we are not at equilibrium, and it's Q. So any point on this line where that ratio is not the one perfect ratio at this one specific temperature, it's Q. So Q is basically like the very millisecond after the reaction starts and you have a tiniest bit of product. And then as you go along until you hit equilibrium, then you're at K. Or again, if someone throws some extra product in there to try to get the reaction going, then again, this goes back to being Q until you reach K. So everything eventually at the specific temperature will reach K. So this is one way we represent it. And the other way we represent it is in a chart format. And so the I stands for initial and the delta stands for change. And so another way and the EQ is equilibrium. So instead of talking about being on that left-hand side of the line, which is where we are, we're over here, we're like, if this is initial, we'll say, okay, well, initially we have some number, and I'm actually going to make up this number, but I'm trying to explain this conceptually. So I have some number of reactants and products. So that's before I start. I'm going to lose some of them to get to equilibrium. Any point between right here, which is when the reaction, like it's the millisecond before the reaction starts, any point between here and any value of X until I reach equilibrium, this is called Q. And as a little note before the reaction, you don't have any reactant and you will be making some as you go along. So Q involves the same ratio as K, the product to the reactant ratio, and it's just when you haven't reached equilibrium yet. So you'll see this kind of a look also when we're talking about equilibrium.